A parabola is a graph of a quadratic equation. And if you recall, a quadratic equation is where the highest power of x is x squared. Now, in this video, I'm going to look at parabolas of the form y equals ax squared. So it's just a coefficient before an x squared. I'm also going to look at ax squared plus or minus a constant, which I'm going to call k. I'll also look at x plus or minus another constant in the bracket, which is squared, and also the final combination, x plus or minus the constant in the bracket squared, plus or minus another constant. So this video will look at these forms of the graph so that you'll be able to then graph any of these. There's a second video, and that deals with graphs of the form ax squared plus bx plus c. So that's in video 2. Let's look at the simplest of these to start with, and this is a y equals x squared graph. And we get this by looking at our x and y values and plotting a table. So if x is 0, then x squared is 0, so y is 0. When x is 1, 1 squared is our y value, which is 1. When x is 2, our y value is 2 squared, which is 4. So that's 4. Not very well to scale this, but you're getting the idea. And so on. So when x is 3, 3 squared, our y is now 9. And if we go in the negative direction, minus 1. Minus 1 squared is just 1. And minus 2. Minus 2 squared is 4. And minus 3 squared is 9. So as you can see, the graph is symmetrical about the y-axis. So therefore, the y-axis is called our axis of symmetry. And it's not always going to be the y-axis. It can vary if the parabola is of a different form, as you will see. Now, the very bottom point is called the vertex. And that is the turning point of the graph. And that's where the gradient is negative. Here it's 0, and then the gradient becomes positive. Now, the shape of this graph is concave up. And we sometimes describe it as a happy face. And you'll understand why in a minute when I show you what happens if we have a y equals minus x squared graph. So if I'm to plot this one, y is minus x squared. For our x values and our y values, we again draw up our table, 0, 1, 2, 3. And we've got 0. 1 squared is 1, minus, so it's minus 1. 2 squared is 4, but it's minus, so it's minus 4. Minus 9, and so on. And if we continue with our negative numbers to have a look what happens on the left side of the axis, we end up with minus 1 squared is 1, but it's minus, so it's now minus 1. Minus 2 squared is 4, but we have to add in another minus, so it's minus 4, and so on. And if you actually plot this one, the shape of it is called concave down. And sometimes we'll describe this as the unhappy face. That's our x and y axis. And we should always label our graphs y equals minus x squared. So the difference in our equation was we had a negative coefficient before the x squared, and that resulted in our concave down shape for our parabola. So So remember, a negative coefficient before the x squared results in a concave down shape on the parabola. Let's have a look at how the different size coefficients affect the graph. So we're moving on to the y equals ax squared. Now I'm going to look at y equals a half x squared and y equals 2x squared. So if I am to plot these, and to plot these I will draw up my table again. Y equals a half x squared and y equals 2x squared. And if x is 0, this is going to work out to be 0, and so is this one. If x is 1, this is going to work out to be a half. This will work out to be 2. When x is 2, that's 2 squared is 4, half of that is 2. 2 squared is 4, times 2 is 8. And if I go in the negative direction, minus 1, it's going to work out to be a half again, and 2. It's going to be 2, and that's going to be 8. And you can see already, again, it's going to be symmetrical around the y-axis. So if I am to plot these, this is what it will look like. So the graphs of these will look like this. I'm going to start by drawing the original y equals x squared graph. And if I am to now plot y equals a half x squared, it's going to end up being a lot shallower. Good to actually plot these numbers. Y equals a half x squared. And thirdly, y equals 2x squared. If you're to plot this on the same graph paper, it will be a much steeper parabola. I'm drawing these very badly. They are supposed to be symmetrical around the y-axis. Y equals 2x squared. But this is just to illustrate that the coefficient determines the steepness of the parabola. So the greater the coefficient, then the steeper it will be. Now let's move on to adding a constant onto our equation. So I'm going to look at y equals x squared plus or minus k. And in particular, I'm going to look at y equals x squared plus 1. I'm going to look at y equals x squared minus 1. I'm also going to look at y equals minus x squared minus 2 and y equals 2 minus x squared. So looking at this first one, y equals x squared plus 1, and plotting this, you could either create a table of x and y values like we did previously and actually plot it out, or you can use a little bit of logic, which is what I'm going to do. And I'm going to say that my y value is always whatever it was when it was squared, x squared, plus 1. So my y value is always what the original x squared graph was, but with 1 added on. And if we look at that, we have our original graph of y equals x squared, our parabola. And whatever our y value is, we are going to simply add 1 to it. So instead of there, it will now be here. There will be there, that will be there, and so on. And the effect is that the graph is shifted up by 1. So that's 1 there. So we have the exact same parabola, but the vertex, remember the turning point, instead of being at the origin as it was previously, is now shifted up to the coordinate 0, 1. And that's the effect of adding 1. It's shifted it in the y direction plus 1 places. Now let's look at the second one, which is y equals x squared minus 1. And we're going to use the same sort of logic. So our x and y axis. And what we've got is we've got our original x squared graph, but our y value, each time we calculate it, we have to take 1 off. So again, this is our original y equals x squared parabola. And what we're doing is the y value is 1 less each time. So instead of here, it's here, instead of there, it's there, and so on. And we end up with a graph which is identical parabola, but it is shifted down by 1 unit. So you can see that the effect of our constant that we're adding or subtracting onto the end of our quadratic equation is to actually affect the y value by shifting the graph in the y direction, either up if the constant is positive or down if the constant is negative. So let's apply this to a slightly harder graph. Let's look at the next one that we're going to look at, which is y equals minus x squared minus 2. Now, we're using exactly the same principle. We're going to think about the original graph, which is y equals minus x squared in this case, which was our unhappy face, or sad face, as some people will call it, or concave down, if you want the correct mathematical term. So we've got our y equals minus x squared graph, and we've got minus 2 at the end of the equation. So the minus 2 is subtracting 2 from each y value. So the effect is it shifts it in the y direction minus 2 places. So our graph is now still our concave down, or our unhappy face, but the vertex is now shifted down minus 2 places. And finally, the last one that we're looking at is y equals 2 minus x squared. Now, this is exactly the same as writing minus x squared plus 2, which is a lot easier to understand and to graph. This first form just tends to confuse people, so it's always a really good idea to rewrite it in this form. And then it's pretty easy to see that we've got our y equals minus x squared graph as our template, if you like. And it's being shifted up 2 places, plus 2. So the y-axis is being shifted up by 2 units, so our parabola is the same graph but shifted up. And so it looks like this. Let's now look at the next form of our parabola. I'm going to look at a constant being added into the bracket with the x. So x plus or minus h all squared. So let's take an example to illustrate this. Let's do x minus 2 all squared. And if we're to graph this, maybe the best way to work it out and to illustrate it is to actually quickly do a little table, and we can plot some points. So when x is 0, y is minus 2 squared, which is 4. When x is 1, 1 minus 2 is minus 1 squared, which is 1. When x is 2, 2 minus 2 is 0, squared is 0. When x is 3, 3 minus 2 is 1 squared, which is 1. And when x is 4, 4 minus 2 is 2, squared becomes 4 again. And if we're to actually plot this, what we actually get is a parabola which is actually shifted 2 places to the right. So the effect of having a constant in the bracket with the x is it shifts the parabola graph in the x direction, and I always tend to think it shifts it in the opposite direction from the sine. So if it's -2, it shifts it +2 places. Now this is opposite from what was happening with our y axis shift. That was in the same direction as the sine of the constant being added. This is the opposite direction. So therefore, if we had, say, y equals x plus 3 all squared, the effect of that would be to shift it 3 places along the x-axis in the x direction, but in the opposite direction of the sine. So this time we're going -3. So that becomes our new vertex for our parabola. So let's just summarize what's actually happening here then. So these were the forms of the equation of the parabola that we were looking at, our quadratic equations. So A, our coefficient, that was affecting the steepness and also the concavity. So it was concave up if it was +a, and it was concave down. Oops, let's just fix up that spelling mistake. Concave down if it's -a. The constant k added or subtracted at the end of our equation had the effect of shifting the graph up if it was +k, or down on the y-axis if it was -k. The effect of the constant h inside the bracket with the x all being squared, that had the effect of shifting the parabola either right if it was -h, or left on the x-axis if it's +h. And the final form is simply a combination of the previous two. The h is going to shift the parabola right or left along the x-axis, and the k is going to shift it up or down in the y direction. So this form is simply a combination of the two. And we'll do a couple of examples now to see how that works. Let's look at graphing these two parabolas. Let's do y equals x plus 4 all squared minus 1. That's our first one. And then secondly, let's do y equals minus all of x plus 4 squared plus 2. So let's look at plotting the first one here. We'll draw our x and y axis. And if we look at this, in the bracket with the x, we've got +4. Now remember, this moves the parabola along the x-axis, but in the opposite direction of the sine. So since it's plus, it goes in the negative x direction 4 places. So we'll say that's -4 there. And the number at the end of the equation, -1, affects the graph along the y-axis, so in the up and down direction. So it's going to shift it down 1 place. So if we make this -1 here, then the vertex of our parabola is going to be at -4, -1. And we can then draw our parabola like this, and the vertex is at -4, -1. And that is that graph there. Now let's look at this one over here. Draw our axes again. Now the first thing I'm going to look at is it's minus x squared. So that minus coefficient gives us a concave down shape. So it's the unhappy face. Now first of all, we'll look at the plus 4 inside the bracket with the x. This shifts it in the x direction, but the opposite way from the sign. So it's minus 4 again. But remember, this time it was actually the unhappy face that we were considering. But this time we've got a plus 2 tacked on at the end, and that has the effect of shifting it in the y direction, the up and down direction, so we go up 2 places. So our vertex is now at minus 4, 2. And draw our parabola like that. So we have a second video on parabolas, and that looks at quadratic equations, ax squared plus bx plus c, and parabolas in that form there. That's video 2 on parabolas.